Hello, friends. Welcome back to my YouTube channel. This is part number 9 of my discussion on the topic of drawing. And in this, I will be discussing a numerical example, which is a sixth on the topic of drawing. So that's why I'm calling this as numerical example number 6. And in this, you learn how to find out time of drawing when drying occurs both in the constant rate period as well as in the falling rate period. So let us begin the discussion. To begin with, let us look at the numerical statement. A batch of wet solids is dried from 25% to 6% moisture content on wet basis. The initial weight of the solid is 160 kg and the drying surface is 1 meter square per 40 kg bone dry solid. The critical moisture content is 20% on dry basis. The drying rate during the constant rate period, it is 0.3 into 10 to the power minus 3 kg per meter square per second. For the falling rate period, the following experimental data is available. So for drying during the falling rate period, they have given us the experimental data. So we have different values of percentage X, and then we also have different values of N into 10 to the power 3. So in this case, capital X, as you know, this is moisture content on dry basis, that is kg moisture per kg dry solid. And capital N is the rate of drying, which in this case is given as kg moisture removed per meter square per second. And what are the various values? Various values for these two quantities, they are given to us. So these are the various values, and then corresponding values for N into 10 to the power 3. We have these values. Now you need to understand how N is given to us. So in this case, if you just think of, or if you just look at the first reading, so value of N into 10 to the power 3, it is 0.3. So that is nothing but N is equal to 0.3 into 10 to the power minus 3. Kg moisture removed per meter square per second. So you need to understand this. That is N is equal to 0.3 into 10 to the power minus 3, 0.266 into 10 to the power minus 3, 0.239 into 10 to the power minus 3. In this way, you have different values of N that are given to us. So basically in this case, we have a batch of wet solids, and it is to be dried from an initial moisture content of 25% to a final moisture content of 6%. These moisture contents, they are given on weight basis. The initial weight of the solid, it is given to us. It is 160 kg. So this is weight of weight sample, which is given to us. It is 160 kg. Then the drying surface is given to us. It is given in this way: 1 meter square per 40 kg bone dry solid. The critical moisture content, it is given to us. It is 20%, and it is given on dry basis. Then the drying rate during constant rate period, it is given to us. It is 0.3 into 10 to the power minus 3 kg per meter square per second. Then only for the falling rate period, they have given the experimental data, where we have different values of percentage X and various values of N. And I have just told you how values of N are given to us. So based on this, we are supposed to find out the time of drying. So I hope what is given to us, it is clear to you. Let us move ahead. Okay, so let us first list what is given to us, given data. So you have drying of wet solids, and in this case, drying is taking place in both constant and falling rate period. Initial moisture content is given to us. we denote that since it is on weight basis, it will be percentage xi, it is 25. Then final moisture content, it is given to us, that is percentage xf, percentage small xf is given to us, it is 6. Then initial weight of the wet solid, that is also given to us. We denote that by MW, yes, and it is 160 kg. Then drying surface, it is given to us. It is given in a different form, and therefore I am denoting it as A dash. So A dash is 1 meter squared per 40 kg bone dry solid. So we will have to convert it to A, the area that is available for dry. Then critical moisture content is given to us. It is given on dry basis, and again it is given as a percentage value. So percentage XC, the critical moisture content, percentage X is 20. Then drying rate in the constant rate period, it is given to us. We are going to denote that by NC, and NC is 0.3 into 10 to the power minus 3 kg per meter square per second. Then experimental data for falling rate period, it is given to us. So we have different values of percentage X and corresponding values of N. In this case, capital X is kg moisture per kg dry solid, and capital N is kg moisture removed per meter square per second. And what are we supposed to find? We have to find out the time for dry. So we have to separately first find out time of drying during the constant rate period, and then we will be finding out time for drying in the falling rate period, and then time in the constant rate period plus time in the falling rate period will be the total time of dry. And we are supposed to report this total time of dry. So I hope what is given to us, it is clear to you. Let us move ahead. Let us quickly understand the approach. So first we are going to find out capital Xi and capital Xf. That is initial moisture content, which is given on weight basis, we will convert it to dry basis. Same is the case with final moisture content. It is given on weight basis, we will convert it on dry basis. So how are you going to do that? For that we have percentage Xi, that is percentage moisture content on weight basis. They are known to us for both initial and final. So we will use these values to find out capital Xi and capital Xf. Then we will find out mass of bone dry solid, which we denote by MDS. And we are going to get that by using small xi and MW, yes, which will be known to us at this point of time. Then we will find out area available for drying, which we denote by capital A, and we are going to get that by using A dash, which is given to us, and MDS, which we find in this step. Then after that, we will find out time in the constant rate period, and for that we can directly use this equation. Theta C is equal to MDS upon A into NC into Xi minus Xc. So all the parameters in the equation, they will be known to us at this point of time, and we just have to use this equation to get theta C. Then we will find time in the falling rate period, and for the falling rate period, experimental data is given to us. The equation for time in falling rate period is theta f is equal to MDS upon A into integration from xf to xc dx upon En. So we need to evaluate this integral, and we are going to use the experimental data for evaluating the integral. And how are you going to do that? We will plot a graph of 1 upon n on the y-axis and capital X on the x-axis. So this graph will give us a curve, and we will find the area under this curve, and this area under the curve between the limits xc and xf this area is nothing but the integral in this equation. So in this way, we have to find out the integral, and then once integral is known to us, we can use this equation to get theta f. Then finally we will find total time, which is theta is equal to theta c plus theta f. That is time of drying in the constant rate period plus time of drying in the falling rate period. So I hope the approach is clear to you. Let us move ahead. Let us start solving this. first, as decided, let us find out capital Xi and capital Xf. Let us first get capital Xi, and we are for that percentage small xi is given to us. So from this we are going to get xi. So xi will be obtained by dividing the percentage value with 100. So xi is equal to percentage xi upon 100. Percentage xi is given to us, it is 25. So xi will be 25 divided by 100, that is 0.25. Then capital Xi, we are going to get it by using small xi. It is small xi divided by 1 minus small xi. So therefore capital Xi is equal to 0.25 divided by 1 minus 0.25. That gives us capital Xi as 0.333. Then let us get capital Xf. For that again percentage small xf is given to us, and we will use that percentage value to first get xf, small xf, and then use small xf to get capital Xf. So percentage small xf is 6. So xf will be 6 upon 100, that is 0.06. Then capital Xf will be small xf divided by 1 minus small xf, that is capital Xf is 0.06 divided by 1 minus 0.06. So therefore capital Xf is 0.068, 0.0638, that is capital Xf. So in this way we have obtained capital Xi and capital Xf. Now let us get mass of bone dry solid, which we will denote by MDS. So MDS is MWS into 1 minus small xi, because small xi is a fraction of moisture in the wet solid. So 1 minus xi will be fraction of the bone dry solid. And if you multiply 1 minus xi, that is fraction of bone dry solid, with mass of wet solid, you are going to get mass of bone dry solid. So MWS, we know it is given to us, it is 160 kg. So therefore MDS is 160 into 1 minus 0.25, that gives us MDS as 120 kg. So mass of bone dry solid, that is MDS, it is 120 kg. Then let us get area available for drying, that is capital A. And for that A dash is given to us. A dash is 1 meter square per 40 kg bone dry solid. So that is nothing but A dash is 0.025 meters square per kg bone dry solid. So if I multiply this quantity 0.025 with the mass of bone dry solid, I will be getting area that is available for dry. So A will be equal to A dash into MDS, and it will be we are going to get it in meters square. So therefore capital A will be equal to 0.025 into 120, and that gives us A as 3 meters square. So therefore area that is available for drying, it is 3 meters square. So in this way we have got capital Xi, capital Xf, we have got mass of bone dry solid, and now we also have got the area that is available for dry. So I hope the steps are clear to you. If you have any doubts, you please mention them in the comment section. Let us move. Now let us get time in constant rate period, and for that we will use this equation. Theta c is equal to MDS upon A into NC into Xi minus Xc. So in this case MDS is 120 kg. We have found this earlier. Then capital A is 3 meters square, that is also known to us. NC it is given to us, it is 0.3 into 10 to the power minus 3 kg per meter square per second. Capital Xi we found out earlier, it is 0.333. Percentage Xc is given to us 20. So therefore Xc will be 20 divided by 100, that is 0.2. And therefore now we can easily use this equation. Theta c will be equal to 120 divided by 3 into 0.3 into 10 to the power minus 3 into 0.333 minus 0.2. So that is theta c is equal to 13333.33 into 0.133 and the product of this quantity is this product is theta c is equal to 17733.33 seconds. So now we have obtained time in the constant rate period, and it is 17733.33 seconds. We can convert this to hours by dividing with 3600, because we know in 1 hour there are 3600 seconds. So by dividing this quantity with 3600, we will be getting theta c in hours. So therefore theta c is equal to 17733.33 divided by 3600 hours. So that is theta c is equal to 4.93 hours. So therefore time required for drying in the constant rate period, it is 4.93 hours. So I hope the steps are clear to you. You just have to use the equation in this case, because all the quantities in the equation, they are known to us, and we can easily find out theta c. If you have not understood any step, you please mention that in the comment section. Let us move ahead. Okay, now let us find out time in the falling rate period. And for that, we will use this equation, or we are going to use this equation. Theta f is equal to m ds upon a into integration from xf to xc dx by n. Now, in this case, the important task is to find out this integral. And for that, we will be using the experimental data that is given to us. So, getting the integral, for that, we will plot 1 upon n on the y-axis and capital X on the x-axis. And if what the curve that we get, we have to find area under that curve between the limits xf and xc, and that area under the curve is nothing but the value of this integral. So percentage x values and n into 10 to the power 3, these values, they are given to us. So I'll quickly list all the values that are given to us, and then first I will get values of x. How? By dividing percentage value with 100. So each of the percentage value that is given to us, we will divide with 100 to get capital X. So accordingly, capital X will be obtained by dividing each of this value with 100. So 10 upon 100 is 0.1, then 9 upon 100 it is 0.09, 8 upon 100 it is 0.08, 7 upon 100 it is 0.07, and 6.4 divided by 100 it is 0.064. Then 1 upon n. So we need 1 upon n. So if you take reciprocal of this, it will be 1 upon n, and reciprocal of 10 to the power 3 will be 10 to the power minus 3. So basically in this case, now we will be getting values of 1 upon n into 10 to the power minus 3. For example, the first value is 3.33. So this is 3.33. So 1 upon n is actually 3.33 into 10 to the power 3. So each of the value that we will be listing over here, we will have to multiply with 10 to the power 3 to get 1 upon n. You please try to understand this. So various values of 1 upon n into 10 to the power minus 3 I am listing. And now we are going to use these values to get this integral. So now the data is ready with us. We just have to plot the graph. Let us move ahead. Okay, now let us plot the graph. So on the x-axis, we will be plotting capital X, and the scale that I have chosen is 1 centimeter is equal to 0.05. On the y-axis, we will be plotting 1 upon n, and the scale is 1 centimeter is equal to 5,000. So if you plot various values of 1 upon n versus x, you get a curve like this. And now we have to find out area under this curve between the limits xc and xf. So our equation is theta f is equal to m ds upon a into integration from xf to xc dx upon n, and we are getting the value for this integral. So the limits are xc, x is 0.2, and the lower limit is xf. xf is 0.064. So we know x is 0.2 and xf is 0.064. So accordingly, I have selected the limits. Now the task is we have to measure the area within this limits. So let us get that area. I will erase it. Okay. So first is for measuring the area, I'm considering the smallest square on this graph. So and first I will find out the area of that smallest square. So you can see over here the smallest square on this graph, and let me just find out area of this. So dimension along x-axis is 0.01 for this square, and dimension along y-axis is 1000. So therefore area of one small square is small a is equal to 0.01 into 1000, that is 10. Now you just have to count number of such small squares within this region. So number of those small squares into area of one small square will give us the total area under the curve, which is nothing but the integral in this equation. So let us count the number of squares. So for counting the number of squares, what I have done, I have selected different regions. So this is what I have used in the solution. You can use a different approach. So for example, first I have selected this region. So I will count number of squares, number of small squares in this region. I will call it as N1, and you can easily find that number of small squares in this selected area is 30. So N1 in this case is 30. Then the next region that I have selected is over here, and within this region number of small square is 16. You can count. Then next I have selected this region. Within this region the number of small square is 9. The next I have selected this region. So within this region number of small squares is 10. Then next I have selected this region. Within this region number of small squares is 4. And then I have selected this region. And I have found out that within this region the number of small squares is 19.5. Because within this orange strip we have 75% of the square. Each square is 75% of the entire square. So that's why the number of squares covered by this orange strip, it is 19.5. And in the remaining region, in the white remaining region, the number of squares is approximately 70. So now if we just have to add all these squares to get the total number of squares, and I will come to know that the total number of squares in this case is 105.5. So you can use an appropriate approach for counting the number of squares, or you can use an appropriate approach to find the area under the curve. And one such approach I have discussed over here. If you have understood it, that is very good. If you have any doubts, you please mention them in the comment section. So at this point of time, now I know that under the curve within these limits there are 105.5 small squares, and each area of each small square is 10. So next we will be getting the total area under the curve, and that will be nothing but the value of this integral. So let us move ahead. Now let us get total area. So I am denoting it as AUC, area under the curve, is equal to total number of squares into area of one small square. So total number of square we just have found out, it is 105.5, and area of each square is 10. So therefore total area under the curve is 105.5 into 10. That is total area under the curve is 1055. So that means the value of the integral, that integral. Which integral? Integration from xf to xc dx upon xn. This is nothing but the area under the curve. Therefore, the value of the integration from xf to xc dx upon n is 1055. Let us continue with this. So now let us find time of drying. Theta f is, we know, mds upon a into the integral. So integration from xf to xc dx upon n, and now we have got value for this integral. So integral from xf to xc dx upon n is 1055. mds is known to us, it is 120 kg. Area is known to us, it is 3 meters square. Therefore, theta f will be 120 into 1055 divided by 3. That gives us theta f as 42,200 seconds. We can convert it to hours by dividing with 3600. So, theta f is 42,200 divided by 3600. So, that is 11.72 hours. So, therefore, time of drying during the falling rate period, it is 11.72 hours. Now, we have to get the total time of drying. Let us get that. So, total time of drying is theta is equal to theta c plus theta f. Theta c is 4.93 hours. We found out it earlier. Then theta f we just got, it is 11.72 hours. Therefore, theta is equal to 4.93 plus 11.72. Therefore, that is theta is 16.65 hours. So, in this way, total time of drying, in this case, it is 16.65 hours. And that is what we have to report in this numerical example. So, with this, we end our discussion. We have got the final answer. And therefore, we end our discussion for this numerical example. I hope you have understood the steps that I have used while solving this numerical example. If you have any doubts, you please mention them in the comment section. For this numerical example, we will stop at this point of time. In my next numerical example, in my next video lecture, I will discuss the same numerical example, but in that case, we will assume that the entire falling rate period is linear. So, hope to see you soon in that video lecture. Thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it, and hope to see you soon in my next video lecture. For now, have a nice day. Bye bye.